Hey class, Mr. Hanji here. For today's lesson, we're going to be taking a look at section 11.2, which is going to deal with proving figures similar with transformations. Now, for today's lesson, we have one learning goal, and our learning goal for today is that you will be able to determine whether two figures are similar using transformations. So, the goal for today is to determine whether or not two shapes are similar, meaning same shape, but not necessarily the same size. So it can include a dilation, so it can be smaller or bigger. It just has to maintain that same shape. Now, the transformations that we can use are dilations, like we talked about in 11.1, and also those transformations back in Module 2 from Geometry A. So reflections, rotations, and translations. So we could rotate a shape, we can reflect it, and we can slide it up, down, left, or right. So that is our goal today, to be able to get one shape to map onto the other by using these four different possibilities. Now, for example 1, they want us to determine whether the two figures are similar using similarity transformations, rotations, reflections, translations, dilations. If so, what is the scale factor of the dilation? So the first thing they're going to ask us to do in example 1 is really just determine if we could get one shape onto the other. And then if we could, they need us to figure out the scale factor. So that's all we have to do for example 1, is just determine if the two shapes are similar, meaning they have the same shape. So the angle measures have to be the same, and you have to have the same scale factor for all of the side lengths. If that is the case, then it's a yes, and then we can figure out that scale factor. So if we look at A, so we have triangle RST and triangle XYZ. Do these two triangles appear to be similar? They do, so we're going to say yes. And for this one, it doesn't appear that we need to rotate it, reflect it, or translate it. All we need to do is dilate it. So we either need to make it bigger or smaller. We're going to consider RST as the original and XYZ as the prime, so the one that's been dilated. So if we're going from RST to XYZ, we have to make it bigger, so we have to increase this size. So that's going to be our dilation. Now, from there, we need to figure out what the scale factor is. So what we talked about in section 11.1 is using a set of points. So we could use R and X, we could use Y and S. Doesn't matter which one you do, just remember it has to be the prime over the original. So if we look at, let's use Y and S. So if we set up a ratio using Y and S, Y is at 3 on the x-axis, and then S is at 1 on the x-axis. So it's going to be 3 over 1, which is going to give us a scale factor of 3. Now we could do the same thing with X and R. X is at 3, R is at 1. So 3 over 1 gives us 3. And then if we did Z and T, Z is at negative 3, T is at negative 1, so negative 3 over negative 1 is also 3. So yes, we could use similarity transformations to determine that these two are similar, and we know that the scale factor for these two shapes is 3. Meaning, if you took this original shape, this original triangle, RST, if we multiplied it by 3, we would get X, Y, and Z. And that is our answer for example 1. Now, For part B of example 1, if we look at triangle JKL and triangle MNP, both of these are triangles, so that is the first thing. The next thing is, do these two appear to be the same shape? Meaning, do they appear to have the same overall angle measures in that we have the same ratio of measures for the side lengths? Well, if we look at angles J and M, okay, angles J and M appear to be a different measure. So that means that these two triangles are not similar. While yes, they are triangles, they do not maintain that property of the same angle measure. So our answer for this is going to be no. And our reason is going to be that angle J is not congruent to angle M. Okay, so what I'm saying is that this angle and this angle do not have the same measure. You could say the same thing for K and N, or L and P. If you look at those, and if you were to actually use a protractor and measure, their angle measures would all be different. So B is going to violate that similarity properties, therefore they are not similar. Alright, and that is our answer for part B. Now for C and D, it's going to be much of the same thing, where we have to determine if the two are similar, and then if we can determine that they are similar, what would that scale factor be? So, if we look at C, so for C we have PQRS, and then we have WXYZ for these two rectangles. So first of all, do these two shapes appear to be similar? Do they appear to be the same shape, have the same angle measure, and just kind of maintain that scale factor for all four sides? Okay, yes, they preserve the angle measure. They appear to be the same shape. The key for this, though, is the scale factor. Is that the same for all of them? So if we were to go through, and if we were to look at the side of PQ and then XY. So if we went through and figured out the length of PQ, that would be 2. And then for XW, that is 1, 2, 3, 4. So if we were figuring out the scale factor, okay, it would be 4 over 2, because prime over the original. So that means our scale factor in this case is 2. Now, if we look at one of the other side lengths to determine that this does follow, if we look at for QR, so for QR, it's 1, 2, 3, 4. If this is a scale factor of 2 for the entire problem, then the side of XY, if it's following the scale factor of 2, if we do 4 times 2, it should give us 8. So that means XY needs to have a length of 8 for it to have this ratio of the side lengths. So if we go through and figure out for XY, it's 1, 2, 3, 4, 5, 6, 7. So if we went through and figured out our ratio, we would end up with 1.75 and not 2 as our scale factor. So, because we have two different numbers for our scale factor, okay, for PQ and RS, if we take these two side lengths and multiply them by 2, we get XW and YZ. But if we take QR and PS and multiply it by 2, we do not get the full length of XY and WZ. So what that means, because I have two different numbers for scale factors, it means that these are not similar. So while it might look like it, it does not mean that it is always the case. So like I did with A, okay, while yes, we determined that these were, in fact, similar, okay, like I went through and did for all the points around, okay, we did y over s and we got 3. If we did x over r, we had 3 over 1, so we had 3 again. So we had it 2 times, and if we checked one more time for z over t, we had -3 over -1, -3, -1, and that gave us 3. So in this case, we had 3 every single time we checked the side lengths for the scale factor, whereas for C, if we go through and check it each time, we get a different number. Okay, I don't get 2 each time, or I don't get 1.75 each time, yet I get a different number. So because that number is not the same, that means that these two are not similar. Yes, it's the same shape. Yes, they have the same angle measures, but we do not have that same ratio for all the side lengths. So because that ratio is not the same, that means that these two are not similar. All right, so if we look at D for CDEF and TUVF, okay, we have to go through and determine if these are similar or not. First thing is that they maintain the same shape and the angle measures are going to be the same. So all we have to do here is determine if we get that same ratio for the scale factors of the side lengths. If we do, then we can say yes, that these two are similar, and then provide our scale factor. So first thing that we're going to do is, because these are parallelograms, okay, I know that top and bottom are the same length, and so are the left and right sides of both of these shapes. So if I go through and figure out for TF is 1, 2, 3. And for CF, it's 1, 2, 3, 4, 5, 6. So if I set up my scale factor, the TUVF, this is our dilated shape. This bigger one is the original. So we're going to have 3 over 6. That means our scale factor is going to be 1/2. Now from there, what we need to do is figure out then for the other side lengths. Now you have to use distance formula to actually go through and measure. For this though, I'm just going to use a point for one of those side lengths. So let's go ahead and use V and E in this case. Okay, V and E occur at the same spot in both of these statements. It's the third letter. So then we're going to use that to help us figure out if these are in fact similar. So V is going to recur at 2 on the x-axis, and E is going to occur at 1. So if we go through and set up our scale factor, we have 1 over 2, and that is simplified as far as can be. So that means in fact that these do have the same scale factor. So yes, these two shapes are similar. So A and D are similar because we were able to find that scale factor for all the side lengths to be the same. B was not similar because the angle measures did not maintain for the both shapes. C, while it maintained the same angle measures and appears to be the same shape, the scale factor for all the side lengths was not the same, as we got 2 and 1.75. So that's how we knew that those two were not similar, and how we knew that A and D were similar. And that is how we do example 1. Now, before we move on to example 2, just one thing to note, that this circle similarity theorem, that all circles are similar. So if you're ever asked to determine if circles are similar, because circles are the same shape all the time, no matter how big or small, they all have 360 degrees as their angle measure, means that they are all similar. Alright, so with that said, let's go ahead and move on to example 2, which is going to be our final example for today. And example 2 is going to have us take it a step further and not just determine if they are similar, but we're going to find that sequence of similarity transformations that maps the first image or the first figure to the second figure, and we also had to provide the coordinate notation for each transformation. So that's that xy goes to x plus 1 comma y minus 2. So if we look at A, for example 2, we are already determined on the fact that these are similar. So you don't have to figure out if they are similar or not. We just have to figure out how you get the one shape to the other. And we can use rotations, reflections, translations, and dilations. Now the beauty of this section, especially with the homework, is they guide you with it. And that's what's happening on the notes here. So if we look at example 2a, so we have A, B, C, D, and E, F, G, H. Okay, so we have these two parallelograms. We have to take this parallelogram and get it to here. Now, they already set up our path where they're telling us to dilate it and then to translate it. So we just have to figure out what we have to dilate it by, and then we have to figure out what we have to translate it. So you don't have to pull out what different transformations you have to do out of thin air. They do give you some guidance. So if we look at these two shapes, we need to figure out how much we need to reduce this shape by to get down to E, F, G, H. So if we looked at the side length of AB, so that's 1, 2, 3, 4 for the length of AB, and then for EF, that's going to be 1, 2. So if we took our scale factor as 2 over 4, that's going to reduce down to 1/2. So that means we have a dilation of 1/2. So that means we have to multiply ABCD by 1/2 to get it down to EFGH. So we have a dilation of 1/2, and that's going to result in the coordinate notation of 1/2 x comma 1/2 y. Whenever you are performing a dilation, once you have figured out that scale factor for the dilation, all you need to do then is take that scale factor and put it in front of x and y, because you're going to multiply x and y by that dilation. Alright, so if we went through and dilated the shape, just to kind of show you where this ends up, so we're going to end up at so if we went through and dilated the shape, we would end up with our new shape right about there. So from there, we have to figure out how to get this down to here. Now, they tell us to use a translation, so that means we're going to slide it to the right or to the left, and then up or down. Remember that x is going to affect it right or left. And then if we change the y, that's going to move it up or down. And then also remember, right and up is going to be a positive direction, whereas left and down is considered a negative direction. So if I were to add 3 to x, it's going to move it to the right 3. If I were to subtract 3 to x, it moves it to the left 3. Same for y, that it moves it up 3 if you add, and then down 3 if you were to subtract. So now that we have dilated this shape, we have the same shape of this one. We just have to figure out how much we have to move it to the right or left and then up or down to get it from here down to here. So if we use the point, let's go with C. So we have to figure out how we get C to G. So we're going to go down and then to the right. So how much did we go down by? We went down 1, 2, 3. And then we went to the right 1, 2. So we went down 3 to the right 2 for our translation. So we went right 2 and then down 3. So having that, we can then also write our coordinate notation. So if we went to the right 3, it's x, or to the right 2, sorry. So we did x plus 2, and then down 3, that means we're going to have y minus 3. And that is going to be our coordinate notation for the translation and the dilation, and that is our answer for part A. So the nice thing about these problems on the homework is they do give you some guidance on what transformation you need to do. From there, you just have to figure out what happened and then write the coordinate notation. So they will give you the transformation, whether it's a reflection, rotation, translation, or dilation. You just have to determine what specific dilation, translation, reflection, or rotation occurred, and then provide that coordinate notation. So if we look at B, they want us to take JKL, so this smaller one, and we want to move it to this RQP. So we have to perform a reflection, a dilation, and then we have to provide or create a rotation. So, reflection. A couple different ways we can reflect. We can reflect over the x or the y-axis. We can reflect over the line y equals x or y equals negative x. For this one, we're just going to reflect it over the line of the x-axis. So we're going to reflect over the x-axis. And if you think back to Module 2, that coordinate notation for reflection over the x-axis is going to be x comma negative y. Now, odds are you probably don't recall all those transformation rules. So if you were to look in the completed or guided notes folder on Google Drive from the Buzz page, you would find those rules provided for you, or you can always email me and I'll be more than happy to send those to you for quick access and a quick look at the coordinate notation for reflections and rotations. So if we reflect over the x-axis, we then end up with our triangle right here. The next thing they want us to do is to go through and dilate it. So we have to take this smaller triangle and make it the same size as this larger one. So the best way we could do is use RP and JL because they're both, those side lengths are on the grid lines. So JL is the length of 1, 2, 3. So that is the original, so it's going to be on the bottom part of our fraction. And then our p is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be 9 over 3 for this dilation. So if we were to go through and simplify that, 9 over 3 is going to simplify to 3. That means we have a dilation of 3. That means we take this triangle and multiply it by 3, and that's going to get us the same size as this triangle. So if we were writing coordinate notation for this, again, dilation, we're just going to put that number in front of x and y. So that would be 3x, comma, 3y. Next, we need to create a rotation, and remember that we rotate 90, 180, 270, and then 360, and we're going to rotate counterclockwise. So that means we have to rotate this either here, 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 or here. Okay, we're not doing clockwise rotations. We're doing counterclockwise. So if I'm trying to get this shape into this quadrant, okay, because that's just going one quadrant, that means that it's a 90-degree counterclockwise rotation. Okay, if we were putting it in this quadrant, it would be a 180-degree because it's 1, 2, so it's 2 quadrants. So 90, 180, 270, and then 360 would be back in here. So because we're just moving it one quadrant counterclockwise, means that it's a 90-degree counterclockwise rotation. And if you were to look at that note sheet on the coordinate notation rules for rotations, that is going to be negative y, comma, x. And that is our answer for part B. So we reflected it over the x-axis, giving us x comma negative y. We dilated it by 3, that means we multiplied by 3, so we got 3x comma 3y. And then we rotated 90 degrees counterclockwise, giving us negative y comma x. So that is how we do parts A and B. I just quickly want to take a look at part C, and then we will call it a day for this lesson. So for part C, we're going to do much of the same thing. So we have TU, VW, and PQRS. So that means we're taking this smaller trapezoid and we're going to try to place it on this larger trapezoid. And all they have asked us to do is to perform a reflection and then a dilation. So we need to reflect this shape and then we need to dilate it. So if we are doing that, our reflection, because we're going from here to here, is going to be over the y-axis. So we're going to reflect over the y-axis. And for the reflection over the y-axis, it's going to be negative x, comma, y. So if we reflect over that axis, we're going to end up with our trapezoid right about there. Then the next thing they want us to do is go through and perform a dilation. So we want to get from this smaller trapezoid to this larger trapezoid size. So we have to figure out how much it has increased or decreased by. Well, if we look at this length right here, that's 1. And since that's the original, that's going to be on the bottom. And then our new shape for this side length, it's going to be 1, 2, 3. Because this is the new and this is the old. Remember, it's new over old, prime over original. So because I have 3 over 1, that means our dilation is 3. So if we have a dilation of 3, that means our coordinate notation is going to be 3x, comma, 3y. And that is our answer for part C. So all we had to do for that one is reflect it over the y-axis, then determine the scale factor to give us our dilation, and that is your answer. And that is all you have to do for part C and example 1 overall. So, or example 2, sorry. So when you get to the homework for these problems, again, they will provide you some guidance that a rotation, dilation, and translation needs to occur. You just have to give what specific rotation, dilation, or translation, and its coordinate notation. So you don't have to determine what order what has to happen. You just have to give the specific rotation, reflection, translation, or dilation. And that is how you're going to do section 11.2 on using similarity transformations to prove figures similar, meaning that they maintain the same shape, same angle measures, that same ratio of the side lengths, so the scale factor has to be the same for all of the side lengths, and that it also is that similar shape. So, with that said, that is it for our lesson today on section 11.2. As always, be sure to reference my completed notes as you work through the homework, or as a reference if you have a question. And as always, you can let me know next time you see me, or shoot me an email if you need help or have a question. Otherwise, that is it for today. Thank you guys for listening. If you need anything, let me know. Otherwise, have a great day, and I will talk to you guys later. All right, bye.